Now, let us discuss some problems, numericals, questions from the topic of this gaseous state, as these questions are important for IIT, JEE mains, advanced and all other competitive examinations. Let us look at the first question. A small bubble rises from the bottom of a lake. Small bubble from the bottom of a lake rises up to the water surface. At the bottom of the lake, the temperature is 8 degrees Celsius and pressure is 6 atmosphere, and at the top the temperature, now this I will call T1, P1, this is T2, is 25 degrees Celsius and pressure is 1 atmosphere. So, when the bubble is raised to the surface, we calculate the final volume of the bubble if its initial volume was 2 ml. Volume of the bubble is, volume of this bubble is 2 ml, and then here it is, what is V2. So, this is a simple question with the formula. Question is seems to be difficult, but solution is very simple. P1 V1 by T1 is equal to P2 V2 by T2, ideal gas equation. So, here pressure is 6 into volume 2 by temperature 8 degrees Celsius. 8 degrees Celsius is nothing but 281 Kelvin. 281 is equal to pressure at the surface 1, volume we have to find, and T2 is 25 degrees Celsius, that is 298 Kelvin. So, from this if you calculate, you will get V2 as 12.72 ml. So, it is a question simple based on the ideal gas equation. P1 V1 by T1 is equal to P2 V2 by T2. So, the answer is now the simplification, if you do, you will get V2 as 12.72 ml. Now, we go to next question, question number 2. In this question, it is given at a certain amount of gas at 25 degrees Celsius and a pressure of 0.8 atmosphere. Temperature is 25 degrees Celsius, that is 298 Kelvin, and a pressure of 0.8 atmosphere is contained in a glass vessel. Suppose that the vessel can withstand a pressure of 2 atmosphere. So, initially the gas is at this pressure and at this temperature. The vessel can withstand a pressure up to 2 atmosphere. So, let me take that maximum pressure that it can withstand, that is P2 as 2 atmosphere. And now, the question is, how high can you raise the temperature of the gas without bursting the vessel? So, basically we have to find out what is T2. So, here in a glass vessel, volume is V. So, in the same glass vessel, initially the pressure is 0.8 atmosphere, temperature is 298 Kelvin. Then this can withstand a pressure of 2 atmosphere, pressure is raised, that means on heating. On heating, because P is proportional to T, on heating the pressure is raised. So, here at a constant volume, P is proportional to T, or P1 by P2 is equal to T1 by T2. So, from this, that 0.8 by 2 is equal to T1 298 Kelvin by T2 is what we have to find. Again, the simplification if you do, then we will get T2 as 472 degrees Celsius. Okay. So, this is how simple questions based on P1 V1 by T1 equal to P2 V2 by T2, or P1 at constant volume P1 by P2 is equal to T1 by T2. This is how we can solve this question. Now, let us go to question number 3. Dry ice is a solid carbon dioxide. Solid CO2 is taken is 0.05 grams of sample of dry ice. Weight of the dry ice is 0.05 grams. Is placed in evacuated vessel of 4.6 liters. Volume of the vessel is 4.6 liters. So, that means here you have a 4.6 liters of vessel. In this a chunk of dry ice. Chunk of dry ice means a piece of dry ice is kept whose weight is 0.05 grams. Then calculate the pressure inside the vessel after all the dry ice has been converted into carbon dioxide. Now, on heating, again on heating all this is converted. Now, carbon dioxide is converted into vapors. So, here this vessel will now all will have carbon dioxide. So, V is equal to 4.6. So, now the question is calculate the pressure inside the vessel after all the carbon dioxide. Now, the temperature is 30 degrees Celsius, that is 303 Kelvin. So, here solid carbon dioxide weight is 0.05, that means number of moles is equal to 0.05 by 44, right, 0.05 by 44. Now, you take PV equal to nRT, pressure is what we have to find out, volume is 4.6 liters, N is 0.055 by 44, R is 0.0821 liter atmosphere, R value all this in all these problems of ideal gas equation PV equal to nRT, as already we discussed in the theory. Here volume is given in liters, pressure we have to find in atmosphere. So, R value we should take it as 0.0821 into temperature is 303 Kelvin. This if you signify, we get pressure as equal to 6.14 into 10 power minus 3 atmosphere. This is the pressure what we get. Okay. Now, let us go for the question number 4. A mixture of helium and neon gases, mixture of helium and neon gases is collected over water at 28 degrees Celsius. Helium and neon over water collected at 28 degrees Celsius. Temperature is 28 degrees Celsius, that is 301 Kelvin, and pressure of 745 mm, 745 mm, that is 745 by 760 atmosphere, because 760 mm is 1 atmosphere. If the partial pressure of helium is 368, partial pressure of helium is 368 mm, what is the partial pressure of neon? Partial pressure of neon is what? And aqueous tension at 28 degrees Celsius is 28.3 mm. So, here in fact no need to convert the pressure into atmosphere, because here what is asked is pressure of helium is given, pressure of neon is to be determined. According to Dalton's law, of partial pressures, P total is equal to P1 plus P2 plus P3, etc. Some of the partial pressures. Here what are the different gases we have? One is helium, another one is neon, and another one that is not mentioned directly, but what we have to understand, because the mixture is collected over water, water vapor also will be present, and the saturated vapor pressure of the water is nothing but what we call it as aqueous tension. So, pressure of water vapor is also what we have to take. So, the total pressure is 745 is equal to 368 plus pressure of neon plus aqueous tension 28.3 mm of mercury. So, this if you take from this, what we can calculate is the pressure of neon gas as 348.7 mm. So, pressure of neon is equal to 348.7 mm, right. This is what actually what we have to do it. Okay. Now, let us go for question number 5. In the question number 5, what is given is nitrogen forms several gaseous oxides. As you know, nitrogen forms different oxides as N2O, NO, N2O3, N2O4, N2O5. N2O4 is nothing but a dimer of NO2 also. Both are same. Okay. So, like this it forms different oxides of gases, or gases of different oxides. One of them has a density of one of the gas is 1.33 gram per liter, right, measured at a pressure of 764 mm of mercury and temperature of 150 degree Celsius. 150 degree Celsius is 150 plus 273. 423 Kelvin. Find the molecular formula of the oxide. Find the molecular formula. For this, what we have to do is, from the given information, that is density, pressure and temperature, what we have to determine is the molecular weight. If we know the molecular weight, then molecular formula is also obviously we can understand. So, to find the molecular weight, the formula what we have is equal to P equal to dRT by M. For an ideal gas, P equal to dRT by M, okay, or M is equal to dRT by P, where M is the molecular mass. Okay. So, M is equal to density 1.33 or 0.0821 and temperature of 423 by pressure. Pressure is 764 mm. 764 by 760, that is in atmosphere. This is equal to 764 by 760 atmosphere. Here from this, if you calculate molecular weight, you will get it as 46. Now, 46 is the weight, molecular weight corresponds to NO2 gas. So, the gas is NO2. So, from the molecular weight, we have to identify what gas it is, right. Now, let us go to the question number 6. Now, in the question number 6, what given is, calculate the relative rates of effusion of oxygen to methane through a container containing oxygen and methane in the mass ratio of 3:2. Here the mass ratio of oxygen to methane is 3:2. Mass ratio of oxygen to methane is 3:2. So, that means if you consider that there are 5 moles of the mixture of gases, then you have 5 grams of the mixture if you have, then in that 3 grams is oxygen and 2 grams is methane. So, therefore, their mole ratio is 3 by 32 is to 2 by 16. 3 by 32 is to 2 by 16. That means, this is 3 by 32 into 16 by 2. So, this is 3 by 4. So, NO2 is to N methane is equal to 3:4. This is the mole ratio. Now, from this mole ratio, what we have to calculate is the relative rates of effusion. Relative rates of effusion RO2 by R methane is equal to NO2 by N methane into root over molecular weight of methane by molecular weight of oxygen. Okay, because R1 by R2 is proportional to N1 by N2, that is their mole ratio, and inversely proportional to molecular weight. The ratio of rates of diffusion R1 by R2 is proportional to the ratio of number of moles, that is rate of diffusion is proportional to number of moles. So, and also inversely proportional to molecular weight. Therefore, square of the molecular weight under square root of molecular weight. Therefore, RO2 by RCH4 is equal to NO2 by NCH4 into root over MCH4 by MO2. This if you take, now this is 3 by 4 is the mole ratio. Now, molecular weight of methane is 16 and molecular weight of oxygen is 32. So, this is equal to 3 by 4 root 2. Okay. So, this is 3 by 4 root 2. So, the answer is second option, 3 by 4 root 2. Okay. Now, let us go to question number 7. And question number what it says is 4 grams of sulfur dioxide gas diffuses from a container in 8 minutes. Time of diffusion is 8 minutes. Mass of helium gas diffusing from the same container over the same time interval is. So, now this is number of moles of SO2 is equal to 4 by 64, that is 1 by 16. 4 grams of sulfur dioxide is its weight. So, number of moles is equal to weight by molecular weight. Sulfur dioxide molecular weight is 64. So, it is 1 by 16. Now, R SO2 by R helium, ratio of rates of diffusion is equal to is nothing but number of moles of gas diffused, NSO2 by N helium, which is equal to root over helium by M SO2. So, NSO2 by N helium, then number of moles of helium is what we have to determine. This is 1 by 16 by number of moles of helium is equal to root over helium 4 sulfur dioxide 64. This is 1 by 4. So, number of moles of helium is equal to 1 by 16 into 4, that is 1 by 4. So, 1 by 4 moles of helium is equal to 1 gram. So, 1 gram is the sulfur helium gas that will diffuse out. So, this is 1 gram. So, our answer is the second option. Now, let us go to question number 8. Now, in the question number 8 what it says is 2 glass tubes A and B at same temperature are connected by very small tube having a stopcock. Bulb A has a volume of 100 cc and contains a gas, while B is empty. On opening the stopcock, the pressure fell down to 20%. The volume of the bulb B is. So, basically the question is like, here you have 2 glass tubes A and B. A is the volume of A is about 100 cubic centimeter, 100 cc. Volume of B is what we have to find out, and here you have a stopcock. When the stopcock is opened, the both are at the same temperature. Bulb A has a volume 100 cc and contain the gas, while bulb B is empty. So, initially suppose if the pressure is P1, now on opening the stopcock, gas diffuses to bulb B. So, initially this is 100 cc. Now, if the volume of this bulb is V, after diffusion the pressure in both the sides will become equal. So, now the question is here P1 V1 is equal to P2 V2. Initial pressure is, let us say P1, then volume is 100. So, 100 into V1, 100 into P1 is equal to P2 is what we have to find, and V2 is 100 plus V. This is negligible volume. This is negligible. So, when the gas diffuses, you will have certain gas over here, certain amount, and certain amount will be diffused over here, and temperature is constant. T is constant, right. So, this is 100 P1 is equal to P2 into 100 plus V1. So, from this what initial pressure is P1, final pressure is P2. Initial volume is 100, final volume is 100 plus V. Okay. Now, the pressure fell down to 20%. That means P2 is 20 P1 by 100. 20% fell down. okay, the pressure fell down to 20%. So, it is 20 P1 by 100. Therefore, 100 into P1 is equal to 20 into P1 by 100 into 100 plus V, right. Now, this if you calculate, then what you will get is, now 20 into 100 plus, so it is 20 100 plus 20 V is equal to 100 into 100, 10,000. So, 20 V is equal to 8,000. So, V is equal to 8,000 by 20, 400 cc. So, the volume of the second bulb is 400 cc. So, the option is, correct option is option 4. Now, let us go to question number 9. Pressure of 1 gram of ideal gas X at 300 Kelvin is 2 atmosphere. Pressure of weight of one gas is 1 gram. Pressure of that 1 gram of an ideal gas X is 2 atmosphere at a temperature of 300 Kelvin. This is for gas X, and for gas Y, another gas Y that is 2 grams is introduced. Then the pressure has become 3 atmospheres. Pressure has become 3 atmosphere. Then the question is correct relationship between the molar masses of X and Y. Temperature is again 300 Kelvin, and the temperature is 300 Kelvin for both. The weights are different and the pressures are different. So, what is the relation? So, is at constant temperature and volume when PV equal to N, so P1 by P2 is equal to N1 by N2. Now, here P1 by P2 is equal to number of moles of X by number of moles of X plus number of moles of Y, because here 2 grams is added, right. So, initially you have only gas X and then Y is added. So, it is Nx plus Ny. So, P1 by P2, that is 2 by 3 is equal to number of moles of gas X, that is 1 by molecular weight of X divided by 1 by molecular weight of X plus 2 by molecular weight of Y. This is what the relation we have to write. 2 by 3 is equal to N1 by N1 plus N2, total number of moles. So, from this if you do the relation, what you get is that molecular weight of Y, you will get it as equal to 4 times of molecular weight of X. So, the correct answer is second option, My is equal to 4 into Mx. Now, we continue with question number 10. The question is, which of the following has maximum density? Density, as we have written the formula, P is equal to dRT by M, P equal to dRT by M, or density is equal to Pm by RT, or D is proportional to P and inversely proportional to T. So, high pressure, high density, low pressure, high density, high pressure and low temperature, high pressure and low temperature. So, among the given 4 options, 25 degrees Celsius 1 atmosphere, 0 degrees is lesser temperature among all the given 4 options, and high pressure is 2 atmosphere. So, high pressure and low temperature, high pressure and low temperature is 0 degrees Celsius and 2 atmospheric pressure. So, it is from this 0 degrees Celsius and 2 atmospheric pressure. This is the condition. So, the correct answer is second option. Now, we go to question number 11. The question is, the density of carbon dioxide at 1 atmospheric pressure and 273 Kelvin is, again density is equal to P equal to dRT by m. So, once again density is equal to P m by RT. Now, in this question the pressure given is what? 1 atmosphere. Molecular weight of carbon dioxide 44 or 0.0821 liter atmosphere per mole per Kelvin, and temperature given is 273 Kelvin. Now, if you solve this, then we will get it as, the density will get it as 1.96 gram per liter. So, the answer is first option, it is 1.96 gram per liter. Now, we go to question number 12. In the question number 12, what again? It is again a question based on the density of a gas. Density of a gas is given as 3.8 gram per liter at STP, 3.8 gram per liter at STP, and the density at 27 degrees Celsius and 7 mm mercury of pressure will be dash. So, say that this is D1, then D2 is equal to what? At the conditions given is 27 degrees Celsius, that is 300 Kelvin, and the pressure is 700 mm, and here STP means you know that it is temperature is 273 Kelvin and pressure is 760 mm. So, once again for same gas D and P relation, as we have written, P equal to dRT by m. So, for same gas D1 by D2 at different conditions, it is equal to, this D is equal to what? Pm by RT. So, that means D is proportional to P by T. So, D1 is equal to P1 by T1. Now, this is T2 by P2, P1 T2 by T1 P2. So, this is density initially is 3.8 by D2 is what we have to find, is equal to P1. P1 is 760, T2 is 300 divided by T1 273 into 700. This if you solve for D2, then D2 you obtain it as 3.185 gram per liter. So, the answer is, correct answer is the option 1, 3.185 gram per liter. Now, we go to question number 13. 1 mole of gas A and 4 moles of gas oxygen is taken inside the vessel. 1 mole of gas A and 4 moles of O2 are taken, mixture is taken inside the vessel, which effuses through a small orifice of the vessel at the same temperature. Then which is the correct percentage of effused volume of gas A and O2 initially respectively? Assume that A does not react with O2, of course, because if it is reactive gases, then it will form some other gas, then it will become a single gas. So, here A is not reactive with oxygen. So, it is a mixture of gases. So, when a mixture of gases is taken, again ratio of rates of diffusion from the mixture, effusion from the mixture is equal to RA by RO2 is equal to NA by NO2 into root over MO2 by MA. So, RA by, now he says what is the correct percentage of effused volumes of gases. So, here what we have to find out is that mole ratio. So, then this is effuses through small orifice of the vessel at the same temperature, then which is correct percentage of effused volume of gases of A and O2. Molar mass of gas is A is 2 grams. So, what we have to find is the ratio of now RA by RO2. So, is equal to what do you call Na by NO2, which is equal to root over, right, molecular weight of oxygen being Now, this is what you call mole ratio is 1 by 4. So, this mole ratio being now Na by NO2 into MO2 by Ma. MO2 is 32, Ma is 2, right. So, Ra by RO2 in turn, this is given as 1 by 4. Mole ratio of A and O2 as 1 by 4. So, it is 1 by 4 in 32 by 2. 32 by 2 is root 16. 16 is 4. So, this is equal to 1 by 4 into 4. So, it is 1. Therefore, ratio of rates of diffusion of Ra to RO2 is same, is equal to 1:1. Okay. So, it is 50% each. It is 50% each, 1:1. Therefore, the correct answer is option 1. Now, in the question number 14, 1 mole of gas X and 2 moles of gas Y enters from the end P and Q of a cylinder respectively. So, if you take a tube, glass tube of cylindrical shape, this is end P and this is end Q. 1 mole of gas X from here, 1 mole of gas X, and from here 2 moles of gas Y are introduced. Then the cylinder has the same area of cross section throughout. So, here the cross section and this cross section are same, because if the cross sections are different, then the ratio at which the two diffuse out will be different. And the length of the cylinder is 150 centimeters. The total length is 150 centimeters, right. And the gas X intermixes with gas Y at some point A. Now, these two are intermixing. Suppose if at some point A, if you take, suppose this is some point A where the gas X and gas Y both are mixing with each other. If the molecular weight of the gas X and Y is 20 and 80 respectively, molecular weight of gas X is 20 and Y is molecular weight of X is 20, molecular weight of Y is 80, 20 and 80 respectively, then what will be the distance of point A from Q? Then he is asking what is this distance is equal to. Now, if this distance, if you consider it as some L, then this distance will be 150 minus L, right. Now, ratio of rates of diffusion Rx by Ry, that is equal to ratio of the rates of diffusion is nothing but the distance by which the two gases travelled, that will give us directly the rate of diffusion, right. So, Rx by Ry is equal to 150 minus L, the distance that it travelled by L, that is the distance travelled by Y, that is equal to root over m2 by m1, molecular weight of Y, that is 80 by 20, that is equal to root 4. So, it is equal to 2. So, 150 minus L is equal to 2L, that means 3L is equal to 150. So, L is equal to 50. So, the distance is 50. So, 150 minus L is equal to 2L, therefore, 3L is equal to 150. So, the L must be 50, that means 50 centimeters. So, from the Y end it is 50 centimeters, then what will be the distance of point A from Q? Distance of point A from Q is 50 centimeters. So, the correct answer is second option, 50 centimeters. Let us take the question number 15. Now, in the question number 50, the given is density of the gaseous mixture in a vessel. What mixture? Methane and helium. Methane and helium mixture in a vessel at 2 atmospheric pressure. Pressure is 2 atmosphere, at a pressure of 2 atmosphere and temperature of 300 Kelvin. Density is given as 0.9756, 0.9756 gram per liter. If a small pinhole is made on the wall of the vessel through which the gas effuses, then which of the following is the correct composition of gases of methane and helium effusing out initially? So, here the composition of the mixture, what is it is asked. So, here density of the mixture is this, and what is the correct composition? So, here first of all the composition of the mixture, to know what we should know is first the number of moles of the two gases, the ratio is what we have to find out. So, now first from this, otherwise from this density what we can find out is the molecular weight of the mixture. So, first density is equal to 0.9756, then molecular weight is P equal to dRT by M, or from this molecular weight of the mixture is equal to dRT by P, right. That if you do it, then this is 0.9756 into 0.0821 into temperature 300 Kelvin by the pressure is 2 atmosphere. This all if you calculate, what you will get is a molecular weight of the mixture. Now, this molecular weight of the mixture is equal to, as the gases are methane and helium, this is equal to, suppose that the molecular weight of mixture means it is the weight of 1 mole of the mixture. In that 1 mole of the mixture, suppose methane is x moles, then x into 16 plus 1 minus x into 4 is what you will get it as a molecular weight of the mixture. This molecular weight of the mixture, on calculation you will get this as 12. This is a molecular weight of the mixture. So, that is molecular weight of the mixture, this is equal to 12. Now, this if you solve, what you will get is this x is equal to what you call 2 by 3. So, when x is equal to 2 by 3, then that means 1 minus x will be equal to 1 by 3. So, that means number of moles of methane by number of moles of helium in the mixture is equal to 2:1. Okay. From this, R methane by R helium is equal to N methane by N helium into root over molecular weight of helium by molecular weight of methane. This all if you do, this is equal to 2 by 1 into root over, this is 4 by 16. So, this is all if you do, this is equal to 1:1. So, that means ratio of rate of diffusion of methane to the helium from the mixture, the initial ratio is 1:1. So, the correct answer is option 1. Now, let us go to question number 16. Now, the question says, at low pressure van der Waals equation is written as P plus A by V square into V is equal to RT. Then the compressibility factor is. So, a van der Waals equation is, here let us just write the van der Waals equation first. Van der Waals equation is P plus A by V square into V minus B is equal to RT for 1 mole of a gas, right. Now, at low pressure volume is very high, so therefore, we neglect B is neglected. When B is neglected, then the equation changes to P plus A by V square into V is equal to RT. Now, this if you expand it, then what we will get is PV plus A by V is equal to RT. Now, compressibility factor Z is equal to PV by RT. So, it is PV by RT is equal to, this PV is equal to RT minus A by V, right. So, it is 1 minus A by RTV. So, 1 minus A by RTV, that is the second option. Second of 1 minus A by RTV is the correct answer. Let us go to question number 17. The gas which can most easily be liquefied is, from the given values of A and B, one can definitely describe, can be easily understand which gas can be liquefied easily. For that, the guiding principle is that, as in the theory also normally we discuss, right. If for a gas with for different gases with different different A and B values, A being a van der Waals constant, which is a measure of A is a measure of intermolecular attractions. A is a measure of intermolecular attractions. Higher the intermolecular attractions, more is the liquefaction. More is the liquefaction or more is the compressibility. The gas can be compressed easily. If interactions are more, then the molecules will come very close and increasing the pressure, or so on compressing, gas can be easily liquefied. Intermolecular attractions are more, gas can be compressed easily. So, as a result, what will happen? So, and A is a measure of intermolecular attraction, we told. Therefore, gas with higher value of A and lower value of B is normally can be liquefied easily, and most preferably it is the higher value of A. So, among the given 4, which gas is having the higher value of A? Anyhow, here the value of B is not given, only A values are given. So, just if you compare only A values as higher value of A is given for ammonia, that is 4.7 among all the 4 answers, 4 options. So, higher value of A is for ammonia. So, is the reason that ammonia is the gas that can be liquefied easily, because in ammonia intermolecular attractions, hydrogen bonding exists. In ammonia hydrogen bonding exists, whereas in other 3 gases, oxygen, nitrogen, methane, hydrogen bond does not exist. So, due to hydrogen bonding, ammonia molecules are very close, attractions are very high. So, ammonia gas can be liquefied easily. So, the correct answer is option 4. Let us go to question number 18. Now, we will see some questions on molecular velocities. So far, we have seen some questions on ideal gas equation, density, pressure. Then we have seen some questions on diffusion, rates of diffusion, initial rate of diffusion, mixture, initial composition of the mixture for diffusion. All these kind of problems is what we have discussed. Now, also in the previous questions we have seen the van der Waals equation and its applications. Now, we see certain questions on the kinetic parameters of the gases, like RMS velocity, average velocity, most probable velocity, kinetic energy. On this also some questions we try to answer. Now, in this 18th question is, so it is a question related to the RMS velocity of gases. The temperature at which the most probable velocity of oxygen is equal to RMS velocity of ozone at 50 degrees Celsius. The question is temperature at which most probable velocity. Cp is equal to under root 2RT by m, most probable velocity of oxygen. So, most probable velocity Cp for oxygen is equal to under root 2RT by 32. Okay. And RMS velocity is equal to under root 3RT by m. So, the RMS velocity for ozone, it is equal to under root 3RT by 48. Then the question is temperature at which the most probable velocity of oxygen is equal to RMS velocity of ozone. So, this is equal to, this is RT by 4 and this is also RT by 4. This is T1, T2 if you take for oxygen and ozone. Now, this is RT1 by 4 and this is RT. So, RT1 by 4 is equal to RT2 by 4 implies T1 must be equal to T2. So, that means at same temperature 50 degrees Celsius, that is 323 Kelvin. So, as T1 is equal to T2, that is equal to 50 degrees Celsius, that is 323 Kelvin. That is the answer. So, at same temperature 323 Kelvin, that is 50 degrees Celsius, ozone will have the same RMS velocity as that of most probable velocity of oxygen. So, the correct option is option number 1. Now, let us look at the question number 19. Question number 19 is again related to the molecular velocities, specifically RMS velocity. Now, in this question it is given that temperature at which RMS velocity of sulfur dioxide is half the RMS velocity of helium. So, RMS velocity, as in the previous question we have seen, it is equal to under root 3 RT by m. So, now RMS velocity, in fact any velocity is inversely velocity in fact itself is proportional to under root T by m. Any velocity, whether it is RMS velocity or most probable velocity or average velocity, any of these velocities, in fact the molecular velocity is proportional to under root T by m, directly proportional to square root of temperature and inversely proportional to square root of molecular weight. Now, so C is proportional to under root T by m. So, RMS velocity of sulfur dioxide is equal to TSO2 by molecular weight, that is 64, and helium is equal to T helium, that is 300 by 4. Now, what the question says is temperature at which RMS velocity of sulfur dioxide, this is half of this, that means root over TSO2, this TSO2 by 64 is equal to half of 300 by 4. So, under root TSO2 by 64 is equal to half of this root 300 by 4. So, from this TSO2 by 64 is equal to 1 by 4 into 300 by 4. So, this is 4. So, temperature of sulfur dioxide must be 1200 Kelvin. Temperature of sulfur dioxide is 1200 Kelvin. So, the answer must be option 4. Now, let us go to question number 20. A SO2 molecule is twice as heavy as oxygen molecule. That is, of course, we know, because molecular weight of sulfur dioxide is 64, which is equal to 2 into molecular weight of O2, that is 32. Okay, that is we know. Hence, at 25 degrees Celsius, the ratio of the average kinetic energy. Average kinetic energy, we give it with 3 by 2 kT. So, where K is a Boltzmann's constant. So, at constant temperature, any gas will have same average kinetic energy. Any gas will have same average kinetic energy at constant temperature, because if T is constant, K is constant and everything is constant. So, the answer must be 1:1. So, the correct answer is the third option.